All right, this question says, a person travels in a car at a speed of 90 meters per second. To get this driver's attention, a stationary police officer shines a spotlight at the car. If the officer is 100 meters behind the car when turning on the spotlight, how long would it take to reach the car, according to the officer's frame of reference? All right, so the thing about 90 meters per second is it's not a significant fraction of the speed of light. So any light clock that person is carrying in their car, like let's say that he's driving the car, okay, and let's say the person does have a light clock with them as they're traveling. So we can put that like here. The speed is 90 meters per second, and if you make a fraction out of that with the speed of light, you get 0.000003. All right, now that's not a significant speed relative to the speed limit of the universe. It would be also written as 0.000003 times c. Okay? So if we were to calculate the Lorentz factor for this, we would use the formula gamma equals 1 over square root 1 minus v squared over c squared. Let's find out what the gamma really would be. It would be 1 over square root of 1 minus 90 meters per second. We'll square that and then divide by 3 times 10 to the 8th meters per second, and then square that. Okay, so my calculator just says it's basically 1. It's not different enough from 1 for the calculator to even give me an answer. So that means that as this car moves to its new position, by the time the light beam goes up and then comes back, the light clock will hardly have moved at all. That's how fast light is, right? So the car might be located here by the time this whole process is over. Okay, so here's the officer, shines the spotlight at the car, and the light gets there so fast that the car hasn't even significantly moved. So to answer this question, we could simply use the formula C equals d over t. Speed of light equals the distance divided by the time. Alright, so the distance would be basically 100 meters. And then we can plug in the speed of light. And the time will be .0000033 seconds. I did find a calculator that was more powerful, and it gave me that as the gamma. All right, so the difference between the proper time and the dilated time here would be basically negligible. So if the proper time was 0.0000033 seconds, the t prime is going to be approximately the same thing. Why would that be? Because we have the formula t prime equals gamma times t. See? But gamma is basically 1. So there we go. The point is that relativistic effects are only really significant once the speeds of the objects get to be very large. They have to be a significant fraction of the speed of light for the idea to even matter. And there are some cases where that happens. One of the biggest would be in outer space. The speeds of planets and stars and things like that can be significant fractions of the speed of light. So relativity is a big issue in that case. And there's many other cases too, especially when very small particles are accelerated. They can be accelerated to significant fractions of the speed of light because they're so small too.